Basically everything boils down to two things: substitution, parts. Let's look at parts. When is it useful? It's useful when we've got this situation. We've got two functions multiplied together, but we can't simply create derivative times function. One of those functions is not the derivative of the other. This tends to be a good way of doing it. Here's a formula. Some people call it the reverse product rule because that's where it comes from. Let's just do a proof. There's my product rule. Write down the first if the second plus write down the second if the first. If I was to now to integrate everything there with respect to x, well, on the left hand side, obviously it goes back to uv. But then I'm saying, well, it'll be the integral of, whilst it's a horrible way of writing it because I've got my variables all mixed up, it's a formula. It's not actually an integration that I'm doing, so it's okay. And now though, we can look at it and say, oh look, those dx's cancel, and we get our formula. When we move that to the other side, we can create an integral of u to v is uv minus the integral of v to u. So we're going to have two things multiplied together. One of those things will be the u, and one of those things will be the dv. That means one of these things we need to differentiate, and another one of those things we need to integrate. So how do I pick it? Well, u, as a guideline, you choose it so the differentiation makes it something simpler to work with. Whereas dv clearly needs to be something we can integrate. I mean, if I can't integrate, there's no point making it dv because that's what I'm trying to do. Let's do something. Integral of x times sine x. So u, something that when I differentiate it, it'll be simpler. It's either x or sine x. Well, if I differentiate x, I get 1. That's certainly simpler. I can differentiate sine x, becomes cos x. Is that really simpler? I've still got a trig function. Well, let's try the other thing. dv, something I can integrate x. Well, I can integrate that, yeah, not a problem. Half x squared. And sine x, I can integrate that as well. Now, probably a good option is to go u equals x, and that'll just become dx. dv sine x, integrate it, I get minus cos x. Now the setting out of this, I always keep it this way. First line is my function, the second line is my derivative. There is a reason for that, right? Because we go uv, so across there, uv minus x dx minus v du. So minus cos x dx minus cos x. I get plus cos x. And then I can integrate that because cos x is a nice simple integral. Log x. Hang on, you might look at that and think, well, it's only one function. Well, actually it is two functions. The other function just happens to be the number 1. So that's why parts is useful for these integrals that we don't actually have an integral for. Now whilst I've said, hey, memorize it, we can actually now go prove it is what I've said it has been. U therefore has to be log x. Du is dx on x. dv is dx. Integrate that, I get x. So uv, x log x, minus the integral of v du, well the x's cancel, I've just got the integral of dx. Integrate that, and there is the standard, in inverted commas, integral that I showed you before. Log x is x log x minus x. That's where it comes from. Let's do a definite one. X e to the negative 7x. Well, if I choose x, differentiate it, it becomes 1. That's simpler. If I had chosen e to the minus 7x, because I am going to use u equals x, then differentiate e to the minus x, you get e to the minus x. It really hasn't made it simpler. Du is dx, so my dv is e to the minus 7x. Integrate that, I get minus a 7th e to the minus 7x. uv, but this time because it's a definite integral, remember we got the values to substitute in. We're going from 0 to 1. And then it will be minus 1/7 e to the minus 7x, so it becomes plus. Whether I substitute in straight away or just leave it to the very end, it doesn't really matter. Sometimes you do it straight away because that whole thing might turn out to be 0 and it just saves me writing it down. This time I've just left it there, I haven't put the limits in yet. I'll integrate the 1/7 e to the minus 7x, and that's minus 1 on 49. Substitute in, and I have my answer. Now this is interesting. E to the x cos x. Differentiate it, it becomes simpler. Okay, differentiate e to the x, I get e to the x. Oh, that's not simpler. Cos x, differentiate cos x, I get minus sin x. Well, that's not simpler. Oh, well, maybe we look at the other criteria. Integrate it, something I can integrate. E to the x, oh, I can integrate that, that's e to the x. Cos x, oh, I can integrate that, that's sin x. So it doesn't really matter. I'll just choose one. I'm going to do e to the x for my u. Du is e to the x dx, v is cos x, and v is sin x. Why did I choose that one? Well, I guess I chose it for the mere fact that when I integrate cos x, I'll get a positive sin x. Whereas if I differentiated cos x, I would have got negative, and I just left it as, I like all positives. Again, it doesn't matter. uv minus the integral of v to u. So now I have to, that's pretty much as difficult as the one I started with. I'm going to have to do parts again. But make sure you go the same way. So in the first one, I went with e to the x for u. So I'm going to have to do it that way again. Otherwise, I'm going to create a circular argument. I'll come back to some statement like, 0 equals 0 or something like that. The du is e to the x dx. V is sin x. Oh well, there, I'm going to get that negative anyway. V is negative cos x, substituting that in. But remember, it's minus this integral. So minus uv, which will be minus e to the x times minus cos x, becomes plus e to the x cos x. You can see you're going to have to be very careful here with your negative signs here. And then minus the integral of v to u, but we're going minus this integral, so it's minus the integral, so it's plus, but it's minus cos x. We end up with minus the integral of e to the x cos x, and that's what we had to integrate originally. Now that's where we look at it, and we don't see it as working out, we see it as an equation. I can move that minus e to the x cos x to the left hand side and say, hey, I've got two lots of the integral, and I know it's e to the x sin x plus e to the x cos x. Therefore, if I divide by 2. Now some people look at this and they think, well, hang on, that feels like a bit of a cheat. Have you actually integrated? Let's just play around with it. Well, yeah, we have. Over here on the right hand side, we did integration. Just there was no more to do over here on the left hand side. It just became an equation to play with. This came up last year. Really nice. They went and proved that 0 is equal to 1. Okay? So they used integration by parts. So they're integrating 1 on x dx. And they decided they were going to do that by parts, even though we know it's just log x. So they said, well, my two functions then are 1 on x and 1. And so they ended up going, right, uv, we end up with 1 plus the integral of 1 on x dx. They said, that's all right, I'll just take away the integral of 1 on x dx from both sides, and we get 0 equals 1. That's a pretty sound argument. Obviously it's wrong, and that's what you had to do. Explain, well, what's wrong with that? Because clearly 0 does not equal 1. So they got to this point. They took away the integral from both sides and said 0 equals 1, and that was the mistake. Yes, you do take away, but what you're left with is the integral of 0. Because if you'd moved that to the other side, you would have had the integral of 1 on x minus 1 on x. And the integral of 0 is a constant. So we're saying, no, what we've just proven is the constant is equal to 1. So when 0 is integrated, you get the constant. Now, it might be 0 in some situations, but in this situation, clearly it's not. So for our one, it should have been 1. And that was the error in their proof of 0 equals 1. So for F.